We're now going to apply what we've learned about steric strain and about how torsional conformations help to relieve that strain to understand something about the energies associated with that relief. Our learning goals for this will be to develop potential energy curves that tell us something about that torsional motion in larger. To begin, let's consider once again what happens when we have an eclipse conformation that involves steric strain. So here are two carbon atoms with large atoms attached undergoing some kind of steric strain. There can be torsion about this carbon-carbon single bond that can relieve that strain, but the steric strain also causes the bond angles to distort. So when those two atoms are eclipsed, it's basically pushing them farther apart, and that act of pushing them farther apart leads to a higher potential energy. They would prefer to be at tetrahedral bond angles as dictated by VSEPR model. So when those big things come in and get in each other's way, we're going to add energy when they are actually eclipsed. In the staggered conformation, that steric strain becomes somewhat relieved. So we see this in sort of a perspective diagram where now those two atoms are no longer bumping right up against each other, and they can have more normal bond angles relative to the VSEPR model. This has happened because we've twisted about that carbon-carbon single bond, and it's led to a lower potential energy conformation. So this gives us a clue as to how we can think about torsional energies as we change that torsional angle between the two carbons. You can think of this also as being kind of like what two people do when they pass through a narrow doorway. If they're both going through at the same time, they might turn sideways in order to avoid bumping into each other, and that's really all in essence that these two large atoms are doing to avoid that steric strain. To illustrate this, let's use ethane as a model. I've drawn here three equivalent staggered conformations of the ethane molecule. In each of these, the rear atom and its three hydrogens are all oriented the same way and numbered 4, 5, and 6. But the front carbon is changed in each of these equivalent conformations. I've started with one at the lower left, then it's moved to the straight up, then it's moved to the lower right in the third of these diagrams. So you can see what we're doing is we're twisting the front carbon relative to the rear carbon by 120 degrees between each. We can also consider the eclipsed conformations of ethane. In this case, the first one on the upper left is relative to the bottom left one by twisting by 60 degrees about that torsion angle. This causes 1 and 4 to be eclipsed, 3 and 5 to be eclipsed, and 2 and 6 to be eclipsed. There are, of course, two other equivalent eclipse conformations shown to the right there as well. What we're seeing in ethane is that when the atoms are all eclipsed, as they are in the upper set, that's 12 kilojoules per mole higher in energy than the three molecules in the lower set, the three conformations in the lower set. So we have used torsion basically to change the potential energy felt by the molecule. So we go up in energy, we go down in energy, up and down and up and down. So in a sense, while we're twisting about that carbon-carbon bond, we're causing the potential energy to go up and down in sort of an oscillating fashion. You can think of this as being a little bit like a turnstile. And when you go through a turnstile, it sticks in place. You have to push it a little bit to get to the next position of the turnstile. So you've had to fight against the energy of getting over some potential energy barrier. So how would this look if we drew a graph of it? Well, here's what it looks like for ethane. And again, I'm drawing that 12 kilojoule per mole is the difference in energy between being in a happy staggered conformation and a sterically strained eclipsed conformation. Now I've labeled the positions on this diagram A, B, C, D, E, and F so that we can relate these to the particular conformations that give rise to these potential energies. So at the very start, we're going to again start with 1 in the lower left. 4, 5, and 6 are always going to be in the same positions, but 1 is in the lower left, 3 is up, and 2 is on the lower right. Okay, when we go over to position A, we see that 1 has moved up to become eclipsed with 4. Okay, so it's that first eclipsed conformation. In this case, all three positions are eclipsed with one another, and that's what leads to the 12 kilojoules per mole higher potential energy. When we go down again to another staggered conformation, we would find 1 pointing straight up now, 2 and 3 have also shifted over by 60 degrees. This staggered conformation is equivalent to the initial conformation, so it will have the same potential energy at the bottom of this oscillating curve. We can continue this analysis and see that every time the molecule is eclipsed, it corresponds to a peak in this oscillation, and every time it is staggered, it corresponds to a valley in this oscillation. So a relatively straightforward thing to understand. Okay, with butane, we're going to have a little bit more complicated situation. Butane is a longer chain, so it has some additional conformations to think about. So this is what butane looks like. We're going to be considering twists about the central carbon-carbon bond, so we actually have, in this case, methyl groups that are attached to the two end carbons about which we're going to undergo that twist. All right, so this is basically a way to understand what we're going to be looking at in butane. We're going to view down that central carbon-carbon bond, and so we would end up with a Venn diagram, a Newman projection that looks something like this, where the methyls are pointing up and pointing down. The one in front is pointing down. So what did the torsional motions look like in this case? Well, here are the various different equivalent conformations. We start in that staggered conformation with methyl down and methyl up. So it's an anti-configure conformation. And when we twist by 60 degrees about that torsion angle, we're now going to have an eclipsed conformation where methyl in both the upper and lower parts are eclipsed with a hydrogen atom, and then there are two hydrogen atoms eclipsed on the lower right. When we further twist this, we'll end up with another staggered conformation, but so that all of the atoms are in between gaps. But notice now in this staggered conformation, I've got the two methyl groups, which are pretty large. I have them closer to one another. They're in a gauche position relative to one another. So this one won't necessarily have the same potential energy as the A conformation. Again, when we twist by 60 degrees, now we're going to have everything eclipsed, but notice what we have this time. We have two pairs of eclipsed hydrogens, but we also have a pair of eclipsed methyl groups. Okay, and they're the biggest thing on this molecule, so that's going to be a very unfavorable eclipsed, very high potential energy conformation corresponding to D. When we twist another 60 degrees, we'll end up with conformation E, where again they're staggered. And I want you to look at E and C, and notice that the relative relationships of these various things that are attached to the carbon atoms that are on the central carbon-carbon bond, that they're relatively equivalent. So in fact, we would expect C and E to have a similar potential energy. Finally, we twist to another eclipsed conformation where, which is labeled F, and again we have two hydrogen methyl group eclipse conformation and hydrogen eclipsed arrangement. So this is going to look a lot like B, and so it will have a similar energy. This is what they look like when we draw these molecular models. So you can see that the one above B and the one above F look very similar. They're mirror images of one another. And the one above C and the one above E are very similar. They're like mirror images of one another. The one where the two methyl groups are anti to one another, that's the lowest energy conformation. When the two methyl groups are eclipsed with one another, that's the highest energy. And then the others are in intermediate energies that will be in between that lowest and highest. So what does this look like? Well, here's a picture of the potential energy diagram for butane rotation, butane torsional conformation. The lowest energy is conformation A. We get back to conformation A at the very end of this 360-degree rotation. The highest energy, the two methyls being eclipsed, corresponds to conformation D. These intermediate energies at B, C, E, and F are all going to be here in between those two extreme energies. And this is what those conformations look like. So once again, you can see that the highest energy D corresponds to the methyl-methyl eclipsed conformation. The lowest energy A corresponds to the anti-methyl-methyl conformation. And the intermediate ones are a maximum if they're eclipsed, and they're a local minimum if they're staggered. So you can go over one small peak at B, down to a minimum at C, back up to the highest peak at D, and then the reverse trend going the other direction. I should note that molecular population tends to favor lower energy, so in a natural sample of butane, we're going to find more of the molecules in the A conformation than we'll find in the C and E conformations. We won't really find any molecules in B, D, and F because they represent maxima, so the molecule doesn't stay there. It tends to prefer places where it's in a local minimum, like A, C, or E.